Okay. What about the mic? Keep the result. All right. Yeah. Okay. So hi, I'm Rafael. I work at Intel currently as a principal engineer, and I have to make a disclaimer right now. So I don't speak for Intel. You know, whatever I say, there may be people at Intel who don't agree with it. Sorry about this. This presentation and some other talks I will give in this conference are basically based on my opinions and as a maintainer of some pieces of kernel code. All right, so then this is an opportunity. So let me recap. For some time, I have been kind of skeptical about using EAS on Intel chips, and I mean the energy part of it mostly. And this is the opportunity to talk about the grounds for my skepticism. And this is all based on documented behavior or design of the hardware. I'm not going to show any results here, it's just like what I know about how hardware works, and which everybody can find out from the web, basically, and then draw their own conclusions. So, okay. First off, energy models, what they are for, and how they are used in the kernel today. So this is to map performance levels to power, the performance level of a CPU or an individual CPU basically to power. So we know when it runs at this performance, how much power this is going to cause to draw. And the scheduler uses it. So basically, because with the assumption that the schedule governor is going to be used by CPU freak, because then when the utilization is known or the task size, I will be talking about task sizes, meaning utilization, because this is the metric you use to measure the task size, basically, right? So if the task size is known, then the schedule knows what frequency, what performance level to use, and then that can be mapped to power, to the energy model, and then the scheduler can decide, you know, what to do based on this. Works like that. It can also be used in other use cases, like for thermal control in the power allocator governor, because through the CPU freak cooling device. But I'm not going to talk about this use case, just about the scheduler use case. All right, so why am I skeptical about using this on Intel hardware? First of all, there are no power numbers to put into an energy model, and that can be overcome to some extent because you can, in principle, set out to measure like power draw on the SoC in various conditions and use that information. Whether or not this is worth doing, you know, that's a matter of discussion. But so this is the first point. Second, the performance levels of CPUs cannot really be chosen by the OS on this hardware. The OS can only ask for a certain performance level, and it may or may not be granted. And even if it has been granted initially, it doesn't really mean that it will be sustained. And you cannot really say in principle how much time it will be sustained. So it is not like it is predictable for the operating system to, and so, you know, now the question is, okay, why, you know, what sense does it make to use another and things that we can't predict. Another thing is, okay, there may be multiple changes of performance levels of different CPUs depending on different conditions within the time in between, things like scheduler ticks. And the OS may not even see those changes.
Yes, I have a question on point number 1. Can I ask you, or no power numbers to put into the model? Are you referring to the opportunistic allocation of power that happens in Intel chips, or is this something else? You say it can be measured, but there is no really, I mean, you know how this consumes. So if you can elaborate on those numbers don't exist, if you can explain.
So yeah, the CPU, you mean an individual CPU or the chip as a whole?
The chip as a whole, of course, yes.
Because, yeah, you can put an energy meter on the wall, for example, and then use those measurements, but you don't know
for the singular core.
For a single CPU, you don't know how it, because the scheduler has to say a task placement. So it considers individual CPUs, it doesn't consider the chip as a whole.
And this is the dichotomy that it's unresolvable.
Yeah, so you don't have a per CPU power numbers.
Intel is a per SoC, the scheduler is per core.
Yeah, which map to different performance levels. I think.
Just say we also don't have per CPU energy meters either on ARM, but we just play with like hot plug and things like that and measure the chip level to see like if I add one more CPU, what's going to be the delta?
Yeah. So that's why I'm saying that this is doable. But now the question is, is there like trying or not? And I'm kind of not convinced that this is worth trying. All right, so let me go back to what I was saying before. So the performance is adjusted very often, and it may be adjusted for multiple times before the OS can notice that something has changed, which is a problem because then it adds up to the predictability statement I made before. CPUs are not independent, but that also is true for ARM processors, I think, right? CPUs are not independent, so if you change a performance level for one CPU, it will affect other CPUs, and in particular, or you need to know how in order to be able to make decisions that benefit from that. Because then you have to know that, if I schedule something on this CPU, then it will change it will cause schedule to select this performance level, and it will change the performance level of the other CPU that is running something already, and then you will have to take all that into account, and then moreover, that is also related to idle states, because it may or may not, whether or not other CPUs are in idle states may or may not affect the power drawn in a given CPUs at a given performance level, and so on. I will be talking about that later. So there is a dynamic mapping between performance levels and power, and it is highly dynamic. It changes at a high rate.
Okay, what do you mean by the last things? Highly dynamic, the power for the same performance level?
So you can, if you choose a performance level, it may cost you more or less power depending on the time when you do that. And a second later, it may be a different number.
But over time, will it average out? I mean, the hardware is not a random number generator. I mean, it is, but not that drastic. It will more or less do the same, presented with the same workload, right?
Well, with the same workload, roughly, yes. Depending on things like ambient temperature and the skin temperature of the system and a couple of other.
I would like to say that all this, we already have similar things with ARM system and more and more. I mean,
Yeah,
not at the same level that you have with Intel chip. But
Okay,
what
so
you're
let me
seeing
continue.
there, we are facing this right now.
So these are like the general problems I can see, and then I'm going to say about about the reasons why they appear. Right now.
One thing you mentioned schedutil. When you run Intel P-state driver with HWP, then schedutil is not involved. Or...
Not involved, yeah.
Okay.
And then actually the hardware decides or what performance level to use, which is then less predictable in this case, right? All right. So the first thing that has to be dealt with is SNP. So SNP is basically means basically oversubscribing the core in order to squeeze some extra performance from it. And if you oversubscribe something, then you get contention, and that leads to basically random behavior. And this means that you can't really say how much performance you will get for an individual SNP sibling, and how much power an individual sibling will draw. You can roughly estimate that for the core as a whole, but you don't know in advance if a given task will get the core as a whole to itself, or it will be running with something else on the same core, and that's why as long as there is SNP, it's hard to even measure the utilization in this case reliably.
Yeah, even with using APF, MPF, you don't have any idea.
So I know
Like that?
so that both siblings are running at the same frequency.
Okay.
So the core is running. I know about how the frequency the core is running, but then I don't know that in advance. I know that after the fact when I have measured it, right? But I cannot really predict if I
tend to agree on that. The only comment that I would say is that right now, when you look at what implemented, there is a policy related to the hybrid Intel system, the scheduler favoring one core.
Oh, I'm going to talk about this.
It's based, I mean, behind that, there is some kind of power or performance relationship. So
it's based on performance. Yeah, it's based on performance relationships, and I will talk about this later. So I have a slide for it.
My point is that for the EES and the energy model, we don't want to be accurate. We want.
Oh yeah,
if we are 80% right, I would say that's a real
right. But then if you with SNP, I don't think you can be 50% right, because then again you are running something you want to run something on a CPU, and if you run it as an SNP sibling, you cannot really say how much of the resources of the core will be allocated for this task, because it depends. You may probably somehow predict the frequency of the core if you know what the other task is doing, but then you don't know they will both share the resources. That will turn out after the fact.
But I think the SMT problem we already have in load balance. Like we consider hardware threads as 1024 capacity. It's extra code to deal with this, to consider them as cores. But I mean, it just as an idea, we could do the same behavior and wake up as well.
Yeah, load balance more or less assumes they get equal shares. I mean, they won't. Who cares?
All right, but fortunately enough.
Sorry, just one comment I wanted to make as well. So all of the energy model stuff is only ever useful in relatively lightly loaded scenarios anyway. So I think we might want to say that if you overcommitted so much that you need to actually make use of multiple siblings on a core, then it might be the point where you should just say, like, don't even bother with energy awareness anyway, because I mean, you're past the point where it's going to make any difference. So
yeah, you have a point. Also, you can disable SNT, which many people do, and for good reasons unrelated to you know, to this the topic today. I will just say, but you can disable SNT. There are also SKUs without SNT. They are like atom only, like Tor only designs that don't contain. So yeah, SNT can be turned off, can be, as you said, it can be like disregarded to some extent and say, hey, if I need to use SNT, that I'm, you know, I'm in the overloaded case anyway. so who cares? You know, if SNT is gone, there still is a problem, which is that the OS doesn't read the on what's going on. So HWP is the current mechanism for driving performance performance scaling on Intel chips. And HWP, this is similar to CPPC in ACPI, but it actually is regarded as an implementation of CPPC. But what it is, it's really a tiny processor running firmware, and which runs in a control loop, and that control loop is very fast and controls things and decides what to do, how to adjust voltages, frequencies, and how much idle CPU idle time will be used based on its own information on the workload and everything. So it basically collects information about workload and uses that to decide to make decisions. And it works on a different time scale than the scheduler in Linux, because it's like it has a microsecond resolution. And it has to work this way because it monitors, among other things, it monitors power, and it has to prevent power spikes from taking place. So it has to be very, very fast running. There is an interface to talk to the thing from the operating system is kind of heavyweight because it's MSRs. Recently, there is an MMIO interface, but only for, so to speak, read-only, so it can provide information to the operating system, but it cannot take commands from it. So that means, well, so a write to the MSR HWP request, which is the MSR used to control this thing, it's per CPU. And the write takes like 200 cycles. So it is a very slow interface from the perspective of the control of the control in the OS on the main CPU. It has many inputs, as I mentioned already. So it takes information from this MSR, but also it has to control the TDP, which is the temperature envelope of the chip. It takes input from RAPL, which are power limits independent of the TDP, based on the same mechanism. From C states, which CPU is in what C state, how much power is available to the other CPUs, and so on. And that's not a complete list. That is just examples of inputs it takes. So it has a lot of inputs. And again, this is kind of a recapitulation. The OS cannot control P-state selection directly. It can only ask this firmware to please select this performance state for the CPU, and it may or may not do it, depending on its own notion about it. So there are modes in which this can be used. One is when the HWP algorithm is allowed to run and do its thing, and the other is with scheduled on top of it. In the latter case, it uses the desired field in the HWP request register, but this is just a hint. It's not a hard, request. So the OS can only kind of influence things. And it doesn't provide information on power, at least directly. So it has an energy model of sorts built in, but it's not in terms of power or energy, but in terms of energy efficiency, which is a kind of different thing. And now, well, the question is, okay, can you run without HWP? Yes, you can. It may not be enabled. Is it practical to run without HWP on hybrid systems for which all of this is relevant? No, it is not. Unfortunately, some information is provided by HWP or by things that are available when HWP is enabled. So, could run without it, but then you could be off by a significant factor in various cases. And the other reason to use it is that it can react to capacity changes that are induced by the platform firmware, for example, and similar. But say you could run without HWP. Oh, one more thing. There are control knobs for HWP that have been given away to user space. There is EPB, which is per package setting, and the values for it range from 0 to 15, so 16 different values. And there is EPP, which is part of HWP, and it is per CPU, and this is a full byte. So basically, this means that if you were to construct an energy model, you have to take those values into account, and that they will inflate the size of it. Because for every different EPP value, there is a different set of the different not a different set, but different mapping from performance to power, basically. There are symmetries because identical CPUs will have identical EPP curves, but then it is a hybrid system, so.
But exposing these to user space is insane because the EPB and EPP are microarch specific.
Well, not really, because the EPP is part of CPPC, and it's actually documented. And also, this has been done already, so it cannot be undone. And especially the user space already uses those things. And yeah.
Is this something where you get feedback from customers saying that this makes sense to set this stuff, or
to set the EPP?
To set the
yeah, it does.
Okay,
so in some scenarios, so actually EPP. So we have experimented with per task EPP in setting in the scheduler, and it turns out that if you use this in combination with some API, which allows user space to provide information regarding, what type of the task is. This can be more significant than task placement in terms of energy usage.
And second question is, if you change those values, are the relative curves of this different CPU types, like performance and efficiency, do they change, or do they just change their curve?
It changes the curve.
Do they swap? Like, does the performance one becomes the efficient one?
It affects the individual CPU for which you can make the adjustment, but it indirectly affects the other CPUs only. Also, when it starts to run, because the distribution of power is different. in this case. So yeah, directly it only affects the. So for example, you can if there is voltage sharing between CPUs, and you adjust an EPP curve for one of them, then it will affect all the CPUs sharing the voltage rail, because then you can't ramp up. So EPP is basically controlling how fast you ramp up the frequency, or how slow, or kind of like that. You can.
But I guess also like only the performance CPUs share the voltage rail, and that if is it not clear?
Yeah, sometimes yes. Generally speaking, yes, but for so I'm going to talk about it a bit later. Okay, but say that we could do without HWP altogether and just stay in the land of P-states control through a different set of registers. There still is a problem with turbo P-state. So you can look at HWP like turbo P-states extended to the whole range of P-states available. And turbo P-states are P-states that are used only when they are available. So opportunistic, and whether or not they are available depends on what the other CPUs do, and it depends on what state. Okay, I'll give an example later on how far this goes. But anyway, they are opportunistic. So if you ask for a turbo P-state, you may or may not be granted. They are unsustainable, and the definition of turbo. It is sustainable, and the unsustainable means that they cannot be sustained forever. But how long they can sustain, it depends. Again, on what the other CPUs do, and on what happens, whether or not any power limits have been set. What if so? What those power limits are, and so on and so on. Yeah. It also kind of depends on what instructions are executed by the CPU, because some instructions are, say, vector instructions, for example. You cannot run at a certain, cannot be executed at certain LTPs and so on.
But this problem is solved by the next level of innovation in the scheduler, right? The IPCC class thing you have?
Yeah, it is addressed to some extent. But it depends on certain amount of assumptions which may or may not be correct. Yeah, but in general depends on the set of instructions that are executed while running the given task, and also there is one more thing that people don't realize often, that IPC may depend on the frequency. So at high frequencies, the IPC may be lower than at low frequencies. And that's because you can ramp up a frequency very high, but it doesn't mean that the internal, the units that actually do things in the CPU will keep up with this ramp up, and then they may not keep up with it, and it's measurable. So you can run a workload that executes a control amount of work, and then see how much of the work is done over time, right? And high frequencies usually is a plateau.
So Anton already mentioned, like EAS is only there for lightly loaded scenarios, and I wonder if, I mean, in those situations we'll never reach turbo states, even though they are.
No, you will, because and now the question is, okay, this is, I didn't put actually bullet point for it. You can ask, okay, how much or what fraction of the P state range are turbo P states? So in the current hardware, it is 50% and more. And on some CPUs, the only guaranteed P state is the lowest one, and the rest of the range is just turbo. So that means, yeah, you cannot say that.
Back to EAS and the comment made by Contant and the energy model. You from ARM are more familiar with this than I am, so if anybody can recall me, energy model is used for task placement at wake up. So and you use it on the hybrid platform, which is a client desktop, laptop, etc. You must, otherwise who gonna tell you where to place your task, right?
Oh,
You're gonna that later.
yeah, I will. I'll be talking about this. Okay.
Just
So-
another comment. So the trouble. So Intel called those unsustainable or like non-guaranteed state turbo states, and on ARM we just described all of the states, and then sometimes you just can't use them. But it's the same thing with different name. Like power capping.
Perhaps.
It's basically exactly the same. Like in some cases you just can't reach certain OPPs on ARM platforms if you have more than X CPUs running at the same time. It's just we live with it.
Yeah. True.
Well, that's not fully true because we don't have such a big problem like they have, like one OPP which is sustainable. It's, well, in thermal reasons, we don't do EAS at all. If you reach that level, I think what the main point here is that what is going in the microarchitectural stuff. This is what we also have publicly available now, the MPAM stuff. We can change the microarchitectural bits in runtime. And then you cannot assume that the power that you have measured will be the same when you run. It's totally different now, runtime. Those modern processors, they change the behavior in no time. It's not like the old days when you can measure and assume that this is the same power. You can run the same workload, different condition later, and this is different.
No. What I'm saying is that even on ARM, we have a whole bunch of OPPs that are described into the energy model table, and whether or not you will be actually able to hit them,
Right.
it depends.
I've never said that those problems are limited to Intel chips.
No, so yeah, exactly. So you can change actually. You can throttle the CPU how much work you can do at one OPP, at the same OPP. You can change that now.
So do you take turbo P states into consideration today when you're scheduling?
Yes. Because this is a full capacity of a CPU, right? Because so unsustainable, what does it mean? Is it tens of seconds? Is it like how much time? It depends. So usually you can, on modern chips, the one core or one CPU turbo P state can be sustained for several seconds. It is quite a bit of time.
So how do you express that today? Like, is it red and you have a table somewhere?
No, we just use this, the max turbo P state as a full capacity of a CPU, and then, it will, at one point it gets saturated. And then it will run at the frequency that it gets.
It just seems if you're able to take it into account before scheduling today,
Yeah,
you should be able to also extend that.
Ricardo is going to talk about this in his capacity topic, which is going to be next after the break, I think. He can say something about it. Yeah, as far as I can say. But yeah, you can take them into account, and but the way we have to use them is basically we have to use them as a full as the max the one core turbo P state becomes the full capacity, and then the utilization is scaled for frequency changes, and so we can kind of get scale invariant utilization, even though turbo P states are used. But this is about utilization, but very different thing. Because power highly depends on voltage, and turbo P states are those P states where you have to ramp up the voltage high. And now it depends, which of them you are influences the voltage and the energy spending on the CPU. And that's why I'm talking about this here. So for performance to power mapping, this really is a problem. Right. So in addition, as I said in the second slide, or on the second slide, there is voltage rails sharing, or generally speaking, sharing of rails of different types between CPUs and other components in the system. So I admit that I should have put a graph of the meteor-like SoC in this slide. I didn't have the time to do this, so sorry about that. But the important thing to maybe know about it in this context is that there are two places where CPUs are located. One place is a so-called SoC die, where there are I/O components, generally speaking. The PCI holds I/O controllers, things like that. Some accelerators and similar. The other piece or place is the CPU die, where the majority of CPUs live. And now CPU die contains all of the high-performance CPUs, so P cores in Intel terminology, and the majority of small cores or E cores in Intel terminology, but two of the E cores are located in the SoC die. And now the E cores that are located in the CPU die go in modules of 4. So there are two modules of 4 E cores. Each module has a voltage regulator and a voltage rail of its own. All of the E cores in this module share this resource. So if you light up the first one, it will increase the power of this module because of ramping up the voltage. But then it can sustain the max, the one CPU turbo P state forever. Then if you run a second one, then it doesn't have to ramp up the voltage anymore. So the cost of running it is lower than, in terms of energy, it's lower than the cost of running the first one. But then both of them cannot sustain one core turbo P state for so long. And then when you add next tasks to this module, they will be running slower and slower. Eventually, at a much lower P state. So this is the voltage sharing between CPUs as an example. The other example is the SoC die with two E cores located in it, because they share a voltage rail with all of the I/O that is included in there. And therefore, if you ramp up P state to a high value, and then there's no other I/O in use or no significant I/O in use, then it will cause the voltage to ramp up. So the cost is high in terms of energy. But, okay, when the user, say, connects an 8K display to it, the voltage ramps up already to the level that that is sufficient to sustain a one core turbo P state. And the cost of running anything there in terms of energy is low, just because the display of a certain property is used. Okay, so that's all the problems. The current situation is that we use ITMP, which I think that is the scheduler extension that was mentioned before. So ITMT was initially invented for favored cores, so cores that can ramp up the frequency higher than the other cores of the same type, and it basically is based on priorities. So the cores or CPUs that can run faster are given higher priorities than the other CPUs, and the scheduler will first put things on the high priority CPUs. Then that's how it goes. Very simple. Generally good for performance. And unfortunately, there is no energy awareness in it, which is a problem. And now, of course, because I'm running out of time, is the question, where do we go from here?
You said on the slide before, ITMT is SMT. It takes SMT into account, like next slide.
Oh yeah, yeah, it takes SMT into account today. So the way it works is that it will put a task on an SMT sibling at the end. So when it's yeah, so initially yes, but then it becomes lower when something starts to run on this first SMT sibling. Okay, so question is, where do we go from here? And I would like to say I have some ideas about it, but I have no time to talk about that. So let's talk about this during a break, maybe, and maybe later. But it needs to be addressed somehow. We had that there is no energy awareness in this ITMT thing, and we need it.
My question is that at the beginning you say we can't predict the power, the clock, and so on. So how can you make any energy aware decision if you can't predict?
That's a good question.
Yeah, I mean that's the point. I mean,
so the hope is that the hardware will be able to tell us something about energy efficiency, at least of relative energy efficiency of different cores in the SoC, and we can use this information. So
that's my point. I mean, and we are back that if you have some kind of, as we mentioned, what we call energy model so far, it's something really raw, not a really precise defined energy model. So either you can't make any prediction, a raw prediction of your power consumption and compute capacity. In this case, we can't make any.
So compute capacity is. Yes, let's just say, but the problem is with power, with the power energy part or power part of the AS. That is very hard. It will be very hard to put together if we attempted to.
In this case, I'm curious to know what will be the policy for you to do some energy aware or power efficient decisions.
So there are two ways. So first of all, we are over, right? Okay, but there's a break now. So I'm going to answer this question, and we will just move the discussion to the hallway. So there are two kind of directions that can be used in principle. So one direction is that the hardware can tell, like, which core is more energy efficient than the other one at the moment, even. Like, you can say, okay, right now, like this, and then we can use this information to make decisions. And it is kind of an energy model, but it doesn't include power numbers. It just is based on energy efficiency information from the hardware. The other approach is based on the observation that maybe small CPUs are always more energy efficient than big CPUs. And maybe if okay, and if that is the case, then you can use this information without using power numbers, because you know that, okay, I can start running on the low end and then overflow when it gets out of capacity. That's another possible approach. Don't start, okay. So all right, fair enough. Thank you.
Thank you.